Okay, we're going to talk about rational functions. Rational functions are formed by basically taking two polynomial functions and dividing them. And this is what this is saying here. A rational function is of the form p of x divided by q of x, where p of x and q of x are both polynomial functions. Now, the behavior of rational functions is very similar to polynomial functions, but with some interesting differences. First of all, you might recognize that when we're dividing, we do have a concern about dividing by zero. If I divide by zero, remember, that's undefined. And so, unlike polynomial functions whose domain is always all real numbers, rational functions' domain sometimes is not all real numbers. And so what is the domain of rational functions? It's all real numbers x such that q of x, right, this polynomial in the denominator, is not zero. If there's any value of x that makes the denominator zero, we would eliminate that value of x from the domain. So those values, by the way, that cause the denominator to be equal to zero, this q of x function, are sometimes called restricted values. So the domain would be everything except restricted values. So the question is, what's happening when we look at the graphs? We think about polynomials. If you remember, their graphs were smooth and continuous. They just went up and down. They had these turning points, these minimums and local minimums and maximums. So what's different about rational functions? Well, I want to investigate two functions that are rational functions. F of x here is 1 divided by x plus 1. Now, 1 is a polynomial function of degree 0. P of x is 1 in this case. The denominator, q of x, is a polynomial of degree 1. And let's just think about this. You can tell me right away, I hope, what value of x will make the function f undefined. What value of x will give us what division by 0 down here? The answer is -1, right? If x is -1 and I add 1, I'm going to get 0 down here. In fact, that's a 0 of the polynomial function q of x, which in this case is x plus 1. So -1 is a restricted value. So what I want to do is just, first of all, numerically look at this. I'm going to use Ti83 Calculator to look at this. If I go in and into the equation editor and type in this function, right? And let's just look at it from a table. I want to set up my table here. So TBL set, I'm going to do that. So I do second and press that button. And I want to put it into ask mode. So for the independent variable. And so I move my cursor by the arrow keys so it highlights ask, and then I hit enter, and it will highlight ask then for me. So I want to keep my dependent variable in auto mode. So independent variable would be, the input would be x, right? X is the independent variable. The output, which is what I compute here, is my dependent variable. So let's go to the table now. So I'm going to do second and hit the graph button, second graph or table. And now I can plug in values of x. Of course, if I plug in -1, and again, make sure when you're plugging in negative numbers, -1, you make sure you use the negative key, don't use subtraction, right? -1. And if I enter that in, what's going to happen? Well, division by 0, I shouldn't get a value, right? In fact, the calculator says error, right? There is no output. And so one thing we know for sure, if I'm graphing this function f, a vertical line at x equal -1 will never hit any part of the graph. There's no output. -1 is not in the domain of this function. In fact, the domain of the function f is all real numbers except -1. But I can see what's happening near -1, right? What's a value that's close to -1? Well, let's try 0. Okay, 0 is close to -1. If I plug in 0 into the function, you can clearly see the output is equal to 1, which is what we get here. But 0 is not equal to -1, obviously, but I can get closer to -1 than 0, right? Like if I do -1/2, whoops, -1/2, what do I get as an output? I get 2. Can I get closer to -1 than that? Yeah, -0.8. That's closer. Can I get closer to -1? Yeah, -0.9. Can I get closer than that? Yeah, negative 0.99. That's getting close. Now, take a look at this. As I get closer to negative 1, you know, my values are slightly getting larger here, right? 1, 2, 5, 10. And I've been going up by what? You know, from 0.5 to 0.8, that's 0.3. I went up 3. 0.8 to 0.9 is 0.1, and I went up 5. What's going to happen when I go to negative 0.9 to negative 0.99? That's only a difference of 0.09 or 9 hundredths. Well, when I do that, notice what happens to the output. It jumps all the way to 100. That's a pretty big jump for a very small change in x. Let me change the value of x now again. Can I get closer to negative 1 than negative 0.99? Yeah, negative 0.999. Now, how much have I changed going from this value to this value? Just what? 0.009 or 9 thousandths. Just an imperceptible amount, right? 9 thousandths. But look what happens when I change that or evaluate that. The output is now 1,000. Again, 10 times more. Okay? So something interesting is happening. The value, as we get closer and closer to negative 1 from one side, the output seems to be getting very, very large. Okay? I can also get close to negative 1. These values are all greater than negative 1. These values are all greater than negative 1. Let me look at approaching negative 1 from below. You know, what's a value less than negative 1? Like, well, negative 2 is less than negative 1. There's my output. Can I get closer to negative 1 than negative 2? Yeah, like negative 1.5. Can I get closer than to negative 1? Yeah, negative 1.1. That's even closer to negative 1. Again, you can see what's happening to the values of the output. They're getting more negative, right? Now let's get closer to negative 1 than negative 1.1. Well, negative 1.01 is closer to negative 1. And notice the change. I've only went from negative 1.1 to negative 1.01. That's a 0.09 hundredths change. That's not very much of a change. But look at the change in output. Again, we see that factor of 10. Let's get a little closer to negative 1. There, that's closer to negative 1. I've only moved 9 thousandths from this input to this input. And look at the output now. Again, it's in absolute value getting larger, but it's getting more and more negative. Okay, so what's really going on here? If I look at the graph of this function, it's right here. You can see right at negative 1, again, if I were to draw a vertical line right at negative 1, let me draw that as a dashed line, just for reference. Right. I would never hit the graph of the function anywhere. But what did we observe is we were getting close to negative 1. At 0, we were 1. At 1.5, we were 2. And so on. As we get closer and closer, the outputs were getting larger and larger. In fact, by the time we get to negative 0.9, remember the output I think was 10. And look at my scale here. Where would 10 be? 10 would be way up, you know, off the screen, off the top here. Right? So the function's shooting up. And then if I move from 0.9 to 0.99, just a little bit closer to negative 1, I jump from from an output of 10 all the way to an output of 100. Think about how rapidly that thing's growing. You know, it's unbounded. Okay. Similarly, we saw from the values less than negative 1, like negative 2, what the output was, and so on. These outputs were getting more and more negative. In fact, by the time I got to negative 1.1, we were at negative 10 way down here. And so we have some interesting behavior. This is not what we would see for a polynomial function, but is a feature that happens a lot with rational functions. If you do the same analysis that we just did to the function f with the function g, look at this function. Can you tell me what is the restricted value? What value is not in the domain of this function? If you said 3, you're correct. Right? When x is 3, we would be dividing by 0. And so that would be undefined and therefore not in the domain of the function. If you do an analysis this time, if you think about it, any value of x I plug in other than 3 is going to give me, whatever number inside the parentheses. But when I square it, what's going to happen? When I square that, it will always be positive. Always be positive. And 1 divided by a positive number is positive. So the output to this function is always positive. But as I get closer and closer to 3, the value, very similar to the way it did here with this function f, as we got close to -1, the values are becoming unbounded, we say. They just are exploding up. In fact, we say it's approaching infinity. The graph of the function g of x is down here. And so again, you see right at x equal 3, which was that restricted value, it's not in the domain of the function, right? We have this feature. And so how can we describe this? We've described it numerically, looked at it graphically. Well, a way that is often used to describe this behavior is as follows. We write this notation, x arrow a with a plus after. This says as x approaches a from the positive side, from above or from the right. And you remember my calculator when I was plugging in numbers greater than -1, I was approaching -1 from the positive side. As we approach x, as x approaches rather a from the negative side, this is the way we write that. So when I was approaching -1 from below, like -2, -1.5, -1.1, and so on. And so what we saw with the first function f, let's get that graph up here if we can. All right. What did we see with the first function f up here? As x got close to -1 from the positive side, so here's -1, x equal -1. As we approach -1 along here from the positive side from above, what was happening to the function? The values were getting bigger and bigger, and they were just increasing without bound, right? We say it's approaching infinity. Okay, infinity is just a concept to indicate that it's unbounded. That the output to this function gets as large as we possibly want it by just simply taking x closer and closer to -1. It's a really strange thing. But this is what we say. As x approaches -1 from the positive side, the function f of x approaches, and we write the infinity symbol. As x approaches -1 from the negative side, as we come from the negative side, from the left here, right, what was happening? It was becoming unbounded, but approaching more and more negative values, right? We say it's approaching negative infinity. For the function g of x, right? On either side, if I approach 3 from the positive side, or as I approach 3 from the negative side, I'm approaching infinity in both cases, and this is the way we indicate that. So we need to give this thing a name. What is this dashed line that I've drawn? Can we give it a name? Yes. The dashed lines that I've drawn for each of these functions are what we call a vertical asymptote. So a line x equal a is a vertical asymptote of a function if the value of the function, the output, the y value, right, is approaching infinity or negative infinity as x approaches a from the positive or negative side. Okay, so going back to these two examples we just looked at, right, x equal -1 is a vertical asymptote for this function f of x. And that's what this line is right here. The equation of a vertical line is x equal. This vertical line, x equal 3. So let's take a look at this. Now, if x equal a is a vertical asymptote of a rational function, then a is a restricted value. So if we have a vertical asymptote, then it has to occur at one of these restricted values. Remember, those are the values that make the denominator 0. However, not all restricted values give rise to vertical asymptotes. I'm going to illustrate with this function here, r of x. Okay, what is the domain of this function? When I ask that question, you're going to say, well, what values of x will make this denominator 0? If there are any such values of x that make this denominator 0, then those values should be excluded from the domain of the function because division by 0 is undefined. So how can I do that? Well, when is this denominator 0? It's going to be helpful if I can factor this quadratic function down here. The polynomial is just degree 2, right? Quadratic. And everyone should be able to factor that. How does that factor? You should be able to factor that, right? Since the coefficient in front of x squared is 1, we've got the product of the two numbers is negative 2, and they add together to give you negative 1. So it's got to be negative 2 and plus 1. So I can clearly see that the domain for the function r of x is all real numbers x such that what x is not equal to negative 1 or 2. Right? If it's negative 1, I've got a problem, and if it's 2, I've got a problem, right? Those are the two problems. Now, if I look at the graph of the function r of x, and we can do this numerically. Let's just do this numerically real quick. Let's see what's happening at these restricted values. So I'm going to go in and enter in this new function, and I'll put it in this form here. So let's clear that one out. X minus 2 divided by, and then notice I need to put this in parentheses, right? X squared minus x minus 2. Okay. And let's go to the table. Okay. Let's delete all these entries out. So let's get close to the negative 1. What's happening as I get close to negative 1? So again, what's close to negative 1? Like negative 1/2, negative 0.9, negative 0.99, negative 0.999. So I'm approaching negative 1 from above, right, coming from values bigger than negative 1. And what's happening? The values are getting bigger and bigger and bigger. And here's the graph right here. You can see that as I approach negative 1, the graph is starting to go up. Similarly, if I approach it from values below, we'll see it's going to minus infinity. And you can plug in values less than negative 1 to see that. And so we have a vertical asymptote right at negative 1. What about at 2? Well, again, if I plug in 2, I'm going to get an error because there's no output. Right? Let's plug in a value close to 2, like 2.1. Okay, so that's pretty close to 2. The output is about 0.32258. Okay. Again, this is rounded off. Keep in mind if you're in the calculator. Whoops. If you're in the calculator and you scroll over this number, you'll actually see the actual unrounded value down here. So they rounded it off to, what, 5 decimal places. But anyways, it's about 0.32258. Okay, let's get closer to 2. What's closer to 2 than 2.1? 2.01 is closer. What's closer to 2 than 2.01? 2.001? I can get even closer, 2.0001. Wow, that's really close. Does it look like the behavior near an asymptote? Are these values getting extremely large? 10 times as big as they were previously, for instance? Well, I mean, they're all, I mean, look at these. I mean, rounded off to, a couple decimal places, they're all about the same, about 0.33, 0.33. So it doesn't look like we have a vertical asymptote. Let's approach 2 from below. What are some values below 2, like 1.9? That's below 2. Can we get a little closer? 1.99, 1.999, 1.9999. That's getting closer and closer. Again, does it look like the values are getting really large? I mean, no. They're staying real close to about 0.33 something, 0.333 or something, right? It seems like we keep adding another 3 in this if we keep going closer. So what's happening? We don't have a vertical asymptote. Okay. What's actually happening, if we look at the graph correctly, is we have a hole in the graph. There's a hole right here. Not a vertical asymptote. Here we have a vertical asymptote. Right? So this is going to be a vertical asymptote. I'll abbreviate vertical asymptote VA of what? X equal negative 1. But this right here is a hole in the graph. Now, let's go back to the formula and see if we can deduce why we've got a vertical asymptote versus a whole. What's the difference? How do we know? Well, notice that when I look at my 2 where I have a whole, there's of course a factor of x minus 2. But do you notice up top there's the same factor of x minus 2? Okay. When you have the same factor in the numerator and denominator, that 0 that you get down here, which is a restricted value, which again is not in the domain of the function, that's going to give rise to a whole. The negative 1, notice the factor x plus 1. There is no x plus 1 factor up here. If there's only the factor for the negative 1, 0, the x plus 1 in the denominator, not in the numerator, that's when you're going to have a vertical asymptote. Okay. In fact, a general guideline you can do is if you have a x equal a and you want to know if it's a vertical asymptote, plug a into the function. If you get the numerator not equal to 0 and the denominator equal to 0, like if I plug in negative 1, I get negative 1 minus 2 is negative 3. Down here I get 0. Negative 3 divided by 0, that's going to tell you have a vertical asymptote if it's a non-zero number divided by 0. On the other hand, if you get a whole, if you plug in, you get both the numerator and denominator equal to 0, right? So if I plug in 2, I get 0 up top and 0 on the bottom. 0 divided by 0 is going to tell us we have a hole in the graph. Notice here that I could simplify this function r of x, this x minus 2 and x minus 2, right? That ratio is equal to 1. And what am I left with? I'm left with just 1 divided by x plus 1. Again, this is provided that x is not equal to 2 for this function. Okay, it's equal to this. Now what's the difference between this function 1 over x plus 2 and the function r of x? Well, this function, if I think of the function y equal to 1 divided by x plus 1, notice its domain is all real numbers except for negative 1. So I could plug 2 in here, right? So if I plug in 2, what do I get? 1 divided by 2 plus 1, I get 1/3. 1/3. Hey, how much is 1/3 as a decimal? It's about 0.333. In fact, that's the coordinates of this hole. The hole's coordinates are 1, 1/3. That's the height, 1/3. And that's how I can get that. So the graph of this function here is exactly the same as this that I've shown here, except the hole gets filled in. If you plug in that hole, that's the graph of this function compared to the original function r of x. Okay, so that's some weird stuff that happens with the rational functions is the vertical asymptote. Okay. On the next video, we're going to take a look at, well, let's actually do that real quick, and then we'll go on to the next topic. Let me look at some examples and see if we can tell whether we have a vertical asymptote. Let's find the vertical asymptotes for the following functions. Okay, so the first thing we're going to do is find the values in the denominator, the values of x that make the denominator 0. And we will then be able to determine the domain and then decide if we have a vertical asymptote or not. So I set that equal to 0. Can you solve for x in that? Sure. Subtract 7, divide by 3. Okay, so the domain is all real numbers except this number, right? So is this going to give us a vertical asymptote? And the answer is yeah, because if I plug in negative 7/3 into this, up top I get negative 7/3 minus 4, and in the bottom I get what? 0. We said that's the value of x that makes the denominator 0. Right? This number up here, right, is not, right, 0. And so when you have not 0 divided by 0 when you plug in, that's going to tell you have a vertical asymptote. So we have a vertical asymptote at x equal negative 7/3. And notice the vertical asymptote has to be written this way, x equal negative 7/3. We don't say negative 7/3 is the vertical asymptote. We say x equal because it's an equation of a vertical line. Let's look at number 2 here. When is the denominator here 0? Well, it's not as easy as above, but we can get there if we factor. So how do we factor this? How does this factor? Again, we talked about again and again about being able to factor. It's imperative that you are able to do this. You can do it by AC method. You can do it by trial and error. I'm going to do it by trial and error. 2x times x I know is what's got to be if I get 2x squared. And then my last two terms multiply to -5, which is a prime number. So I've got a 5 and a 1, here or here. And of course, one has to be positive, one has to be negative. If you look through all those possibilities, there's only 4 different possibilities. Only one is correct, and it's this one. Notice the outer gives me -10x, and the inner plus 1x. That adds to -9x. So now I've got this factored. And we can tell then what are the zeros. 2x plus 1 equals 0 when 2x is -1, or x is what? -1/2. Or what? X minus 5 is 0 when x is 5. So these are our two zeros in the denominator. Those are restricted values. These are not in the domain of the function g. Do we have vertical asymptotes for those values? Well, let's see. At -1/2, what do I get if I plug in -1/2? 7 times -1/2 is -3.5. What do I get in the denominator? 0. Right? So again, this is undefined. This is not a real number, but this tells me that I have a vertical asymptote at x equal -1/2. What about if I plug in 5 here? 7 times 5 is 35. Of course, I'll get 0 in the denominator again, right? So again, this form tells me I have vertical asymptotes. So vertical asymptotes, x equal -1/2 and x equal 5. Those are my two vertical asymptotes I have. Let's look at one more example, and then we'll stop this video and look at something in the next. So in this one, for what values of x will the denominator be 0? Well, someone might say x equal 1, and you'd be correct, but that's not the only value. I hope you know the other value of x. Again, the easiest way, again, is to factor. Can you factor that denominator? How does that factor? X squared minus 1. I hope you recognize that as the difference of squares. It factors as x plus 1 times x minus 1. Again, being able to factor is essential. You'll need to continue to get better at that if you've had problems with that. Okay. Now let's take a look at this. So we see that x equal plus or minus 1 are restricted values. So these could give rise to vertical asymptotes. So let's see what happens. What's h of -1 equal to? Okay. If I plug in -1 up here, I get 5 times -1 squared is positive 1. 5 minus 5 times a -1, that's a -5. 5 minus a -5 is 5 plus 5, or 10. In the bottom I get, of course, 0. And so that tells me that x equal -1 is a vertical asymptote. What about 1 if I plug in 1? Well, what happens if I plug in 1? The denominator we know is 0. What about here? 5 times 1 squared is 5 times 1 is 5. 5 times 1 is 5. What's 5 minus 5? 5 minus 5 is 0. All right. Now this, right, tells us what? That both the numerator and denominator being 0 tells us we don't have a vertical asymptote. In fact, we have what? Remember? There's a hole at x equal 1. There's a hole at x equal 1. And let's go back up here. If you think about it, you could have we could have factored this numerator here. I'll just say this numerator here could be factored. Right? How can you factor it? What's the GCF? GCF is 5x. I can pull a 5x out. That leaves me 1x for the 5x squared and a 1 for the 5x. Do you notice something now? What common factor do we have in the numerator and the denominator? An x minus 1. Right? And so that tells me, right, I'm going to get that 0 over 0 form, and that 0 over 0 form when I plug in 1. And that's going to tell me that I have a hole in the graph when I have the same factor. Notice the x plus 1, which the 0, -1 came from, there's no factor of x plus 1 in the numerator. So that's why we have vertical asymptote. Okay. So now that we've talked about vertical asymptotes, in the next video we'll talk about horizontal asymptotes.